Alright, hello physics class. Today we're going to be working on two problems that have to deal with the conservation of energy in a system. The two we're going to be focusing on are 10.11 and 10.12. These are both isolated systems, so there's going to be no transfer of energy into or out of the system that we look at. Let's take a look at the first one. In the first problem, we have a person sliding down a water slide. And there's some information we're given about the person's initial state, and we're asked to predict the final velocity. So v final at the bottom of the slide is unknown, and there's a couple things we know about this person's situation. First is that they are 9 meters above the ground. Right? So that's important. Second thing is that their initial velocity, their v initial, is equal to 2.0 meters per second. All right, so we have two givens and one unknown, and let's take a second to think about this conceptually. So, from what we know about energy, the energy that has to do with an object's height is potential energy due to gravity, also known as U sub g. This person is 9 meters off the ground. They're going to have a very high or a relatively high potential energy. As they slide down the slide, they're going to be moving faster and faster, accelerating, and that potential energy is going to be converted into kinetic energy. All right. So what we're going to try and quantify is how fast they are going based on how much potential energy the person had initially. So here's how we can do that. Let's go ahead and write our equation for conservation of energy in a system. We have U sub g final, so the final amount of potential energy, plus K final, or the final amount of kinetic energy, is going to be equal to the initial amount of potential energy plus the initial amount of kinetic energy. All this equation is saying is that the final state of the individual, so their final state at the bottom of the slide, is going to have the same amount of energy as their initial state at the top. The energy is going to look differently. It's going to be potential first and then mostly kinetic, but the energy amount is going to be the same because energy is conserved. So let's go ahead and expand out what these equations mean. So U sub g is equal to the height times the acceleration due to gravity times the mass. All right, we know this from earlier in the chapter. K sub, well, it doesn't matter if it's final or initial, so just K for kinetic energy is going to equal 1/2 the mass times the velocity squared. Let's go ahead and plug these into our equation here. So we have YGM final plus 1/2 MV final squared is going to be equal to YGM initial, and I'll go ahead and erase this for more space, plus 1/2 MV initial squared. All right, so let's go ahead and take a look and see if we can deduce anything from this equation. Potential energy is interesting, so let's go ahead and look at this first variable. Now, and when they're at the bottom of the slide, what is their height going to be equal to? It's going to be equal to 0. So if they start here at 0 and they go 9 meters up, then their final height is going to be 0. That means that at the bottom, this entire value for potential energy is going to equal 0. So we're going to have no potential energy at the bottom of the slide. It's going to be all converted into kinetic energy. So that's a good cancellation. Now, the second thing you might notice is that we weren't given a mass. We were given the height, we were given the initial velocity, but we weren't given a mass, and mass is a part of this formula. So there's something we can do about that. If we were to divide by the mass, it would cancel out of the problem. So if you notice, each and every one of these variables or values has a mass involved. So if we were to divide this whole thing by m, do it to both sides, like in algebra, the masses cancel, and we're left with 1/2 v final squared is equal to y times gravity plus 1/2 v initial squared, right? So we're moving right along, and we just need a little bit more to get v final by itself. So first thing is going to be to cancel out this half by multiplying by 2. So we multiply this by 2, it cancels, and we have to do it to the other side. So that means we go v final squared is equal to 2 yg plus 1, because 2 times 1/2 is 1. So 1 v initial squared. All right, and then the last thing we do is take the square root of the final velocity so that these squares cancel, and that gives us the final equation. V final is going to equal the square root of 2 times the height times acceleration due to gravity plus the initial value squared. Okay, so that's going to be our equation. All right. Now let's go ahead and erase this and plug in our known values. All right, so we have the square root. We're looking for v final, and we know we need 2 times the height, which is 9 meters per second, 9.0 meters, sorry. The acceleration due to gravity, 9.8 meters per second squared, plus 2.0 meters per second, the initial speed, squared. All right, so just a quick note, make sure to keep these straight, that this value here is going to be squared. This value, the square is part of the unit. So if it helps you to put this in parentheses to know to square it, go ahead and do that. But we should multiply 2 times 9 times 9.8. All right, and then we should add together multiply together 2 squared and add that to our values, take the square root of the whole thing. And that should give us 13 meters per second. So v final should equal 13 meters per second. Okay, so a little bit of deduction involved, a little bit of critical thinking, but the important thing is the concept that these are going to equal each other, the final state and the initial state. Choosing what the energy transformation is. So in this case, the energy transformation was potential energy to kinetic energy. And then being able to do the algebra